Okay, hi everybody. So this video I'm going to go through chapter 19, except for all of the learning checks. We will do the learning checks in person together. So chapter 19 is called electrochemistry, all about how electricity and chemistry are related. We'll go through a few of these sections, which are listed here. Let's go ahead and start with 19.1, which is a bit of a review of redox reactions. One thing that's new is that we'll learn how to write half reactions from an overall redox, and then we'll talk about oxidizing and reducing agents. But a little bit of intro to electrochemistry. So electrochemistry is the branch of chemistry focused on the relationship between electricity and chemistry. This involves redox reactions to create electricity, or electricity that will cause non-spontaneous electron transfer reactions to occur. Redox reactions, this is something we covered in Gen Chem 1, just the definition of them. These always involve the simultaneous oxidation of one reactant and reduction of another. We'll remind ourselves what that means. Okay, so a bit of an intro and review. Let's talk about what oxidation and reduction is. Oxidation is the increase in oxidation state. So that's what we mean by oxidation. If something increases in oxidation state, it has been oxidized. This means its oxidation state becomes more positive. And this happens by losing electrons. Remember, electrons are negatively charged, so if something loses electrons, it will become more positive. Reduction refers to a decrease in oxidation state or becoming more negative, and that is achieved through gaining electrons. So in all redox reactions, electrons are transferred. The thing that loses electrons is oxidized. What gains electrons is reduced. We talked about how to identify oxidation states also in Gen Chem 1, so this is another review. Sometimes they're called oxidation numbers. This is a way to bookkeep or keep track of electrons in electron transfer reactions or in redox reactions. So these are our rules. A neutral element that's not part of a compound has an oxidation state of 0. This also includes diatomics. Like hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodide. So these exist naturally as a diatomic, and so any of these in their gaseous states as a diatomic have an oxidation state of 0. Monoatomic ions have oxidation states equal to their ionic charge. The sum of oxidation states in any formula is equal to the overall charge on that formula. Oxygen tends to have an oxidation state of -2. And then hydrogen tends to have an oxidation state of +1. So these are some rules to kind of first just get started with identifying oxidation states. We did this first learning check in class on Wednesday. So I've got these answers here. Magnesium is 0, that's from rule 1. Phosphorus with a -3 charge, that is, I think that was rule 2, that's a monoatomic ion, so its oxidation state is the same as its charge. In an ionic compound, we can follow, especially for simpler ones, like only 2 different atoms here, we can follow ionic charges. We know chlorine is pretty much always -1, and so iron should be +3 here since there are 3 chlorines. All right, the next 2 learning checks we're skipping, we'll do those in class. Feel free to try them, but this is what we're going to do in class altogether. Same thing with this, identifying what's oxidized and reduced. Now let's talk about half reactions. We can separate redox reactions into two half reactions. One depicts reduction, and the other depicts the oxidation. So, for example, in this example reaction, we have, it says AlCl3 aluminum trichloride is synthesized from aluminum and chlorine. So this reaction, we can write this out as aluminum, which is a metal, so that would just on its own. Cl2, the diatomic gas, these combine together to form AlCl3. To write the half reactions, we need to know what is oxidized and what is reduced. So let's identify oxidation states. Aluminum, monoatomic element, we'll assume it's in its natural state, has an oxidation state of 0. Chlorine, diatomic, natural state, oxidation state of 0. In the ionic compound, chlorine would have a charge and an oxidation state of -1. That gives aluminum a +3 oxidation state. So aluminum is oxidized from aluminum without an oxidation state of 0 to aluminum 3+, and then chlorine is reduced from Cl2 to Cl-. So the oxidation half reaction we start with the aluminum reactant. It becomes aluminum 3+, and in this process has lost 3 electrons. We just think about one atom at a time. So one aluminum reactant has lost 3 electrons to become aluminum 3+. So we think about separating the 3 electrons from here, and those are the two things on the product side. This is the oxidation half reaction for aluminum. Let's do the reduction half reaction for chlorine. Now we keep diatomics together, so chlorine will be still listed as Cl2. Notice that we separated aluminum from aluminum chloride when we wrote the half reaction, which we would do. We just don't separate the diatomics. Now chlorine's getting reduced. That means it's gaining electrons. And so electrons will be on the reactant side. Chlorine plus electrons is going to form Cl-. But we need to balance the equation. We have 2 chlorines on the left. We need 2 chlorines on the right, so that will become a coefficient. And then if each chlorine gains 1 electron, then to balance this again, we need a 2 in front of the electrons. We have 2 chlorine atoms. That's part of the diatomic. Each one gains 1 electron, so 2 electrons, and we form 2 Cl-. Now, if you start with half reactions, like we did here, and then combine them, they are combined in a way where electrons gained and lost are equal. So if we just copy down the 2 half reactions that we just wrote, so we have aluminum forms Al3+ and 3 electrons, and then chlorine gains 2 electrons to become 2 Cl-. Now, to gather the overall redox reaction with electrons balanced, actually I'm not going to use this line yet. Electrons gained and lost have to be equal, and right now we have 3 lost but 2 gained. So this is not a balanced redox reaction if we were to just add it as is. we need to multiply coefficients to reach the lowest common multiple. We'll talk about what that is. And the goal here is to achieve the same coefficient in front of electrons on the reactant side and the product side. So right now we have 2 electrons. If we were to just add these together, I guess I will use this. Let's just show what this would look like. We have Al, Cl2, 2 electrons, Al3 plus, 2 Cl minus. I'm going to erase this in a moment because it's not balanced. And then 3 electrons. Okay, so that's just putting all the reactants on one side, all the products on one side. Right now, electrons are not balanced. We need those numbers, the coefficients for electrons, to be equal. So let's go back. I'm going to erase what I just wrote and multiply coefficients so that we get the same number. So we have 3 and 2 electrons. The least common multiple between 3 and 2 is 6. So we need to multiply the aluminum half reaction, all the coefficients, by 2, and the chlorine half reaction, all the coefficients, by 3. So if we do that, I'll rewrite down here. We would have 2 aluminum, 2 aluminum, 3 plus, and 6 electrons, and then 3 Cl2, 6 electrons, 6 Cl minus. Now we have the same number of electrons on both sides. So when we combine it, that is a balanced redox reaction. To combine, we could write 2 Al plus 3 Cl2. We can cancel out electrons now. We have 2 Al3 plus and 6 Cl minus. This is combined half reaction. This is redox reaction, and it is balanced. The balancing has to do with both the atoms and the electrons when we're balancing an redox reaction. Okay, next slide is a learning check, so we'll skip this and do it in class. And the next slide, and the next slide. So we'll go to 19.4 now. These sections are about voltaic cells and cell potential, so I've combined them here. We'll talk about voltaic cells, we'll calculate cell potential, and then we'll talk about different substances that are good oxidizing or reducing agents. Okay, so there are 2 main types of electrochemical cells. There are voltaic cells. Think volt, like voltage. Like a 9-volt battery. These use spontaneous chemical reactions to create a flow of electrons. This is what batteries do. A battery, inside the battery, there is a chemical reaction, there is a redox reaction, and that produces a flow of electrons, and that powers devices. So small batteries, like you put in your flashlight, are voltaic cells. Large batteries that power much larger machinery, those can be voltaic cells as well. There are also electrolytic cells. We are mostly focusing on voltaic cells in our class, but electrolytic cells use electricity to cause non-spontaneous chemical reactions to occur. Either way, both of these involve redox reactions that are thought about and can be separated into these half reactions. And they are physically separated. Okay. So voltaic cells use chemical reactions to create electricity. If a bar of zinc, and we'll look at a picture of this on the next slide, feel free to flip forward. If a bar of zinc is placed into a solution with copper 2+ ions, so you have a solution, copper 2+, and then you add solid zinc into it, zinc atoms will give electrons to copper. So zinc is oxidized to zinc 2+. Copper 2+ would gain electrons and become neutral copper. And so here's the net ionic equation. Copper 2+, which was in solution, add the zinc solid. 2 electrons will be lost by zinc, gained by copper. Zinc becomes zinc 2+, and then copper becomes solid copper. This reaction occurs even when the zinc bar and the copper solution are in separate containers. As long as there is a connection for the flow of electrons and the flow of ions, this reaction can still occur. And this is called the Daniell cell. So here's what that would look like. We have electrons from the zinc bar move through a wire. So this is electricity essentially. And a copper bar to the copper ions in solution. A salt bridge, so this will balance the charge. This is just nitrate, which we know is a neutral ion. Same with potassium. They don't affect basicity or acidity. They're very inactive in solution, so these would be used to balance charge. So zinc can become zinc 2+, copper 2+, becoming copper. So let's talk a little bit more about this. This is a type of voltaic cell, so let's talk about a little bit more about it here. Lots of language which you may have heard in lab already, but if not, we'll talk about it here. So the metal bars where redox reactions take place, this is where, and I put this picture again over here. These are these metal bars, the zinc and the copper, where zinc is becoming zinc 2+ in solution, copper 2+ in solution is being plated again onto that bar. These are called electrodes. The source of the electrons is the negative electrode. This is called the anode. This is where oxidation occurs. So notice oxidation occurs at the anode. This is the zinc side. Zinc is becoming zinc 2+, that's getting oxidized. Electrons are removed from the zinc atom. They can go through the salt bridge and then gained by the copper 2+. So that's where oxidation occurs. Electrons move through the wire towards the positive electrode. The positive electrode is called the cathode. Notice the prefixes here align with anion and cation. Anion for negative. Negative electrode is the anode. Cation, positive. Positive electrode is the cathode. This is where reduction occurs. So with extra electrons there flowing from zinc, copper in solution can gain electrons and become copper. To prevent the buildup of negative charge in the cathode compartment, so to prevent too many electrons over here, inert ions from a salt bridge, so that's what this is, they flow toward respective compartments. So we have potassium balancing out negative charge here and NO3- over there. Okay, a little bit more about voltaic cells. The wire and the salt bridge, so that is this wire where electrons transfer and the salt bridge where we have the counter ions. These are what complete the electrical circuit. Electricity is produced by the movement of electrons through the wire from the anode half cell, we'll call this a half cell, as in this area, to the cathode half cell as the reactants transfer electrons to form products. The driving force for the flow of electrons is the electrical potential or electromotive force, EMF. The electromotive force is measured in volts. So for all voltaic cells, both oxidation and reduction take place at the same time, but not in the same place. But the same overall reaction is taking place as if the two reactants were in direct contact. This reaction has to be spontaneous for a voltaic cell to produce a voltage. Electrons move from the anode to the cathode spontaneously. And then the chemical energy of the reaction is transformed into electrical energy, which can then be further transformed into light, for example, for like a flashlight, or mechanical energy for something to move that uses batteries, like a remote control car. Some more background foundational information here. Voltaic cells produce a flow of electrons by separating redox reaction into half reactions connected by a wire and a salt bridge. So that's what we just learned about. The electromotive force associated with the flow of electrons is measured as the cell potential or the voltage. And then each unique combination of half reactions has its own cell potential. So the cell potential, the voltage, is dependent on what half reactions are occurring, what is present in the anode, what's present in the cathode, or each of those regions of the voltaic cell. So we can measure cell potential, relating it to a certain half cell that chemists chose and set that voltage at 0. So it's all relative to that standard hydrogen electrode. The standard half cell that was used to set a voltage at 0, essentially like setting a norm. This is going to be 0. Anything higher by some amount, that's what we're measuring. So the standard half cell is called the standard hydrogen electrode, the SHE. Standard reduction potentials for different redox reactions, they are represented by capital E, degree symbol for standard, and then RED for reduction. These are this standard reduction potential for different redox reactions. For the half cell reaction is measured with the standard hydrogen electrode as the other half cell. So these are stated values, again, a reference that you can use to solve problems. So we'll see examples. Here's the standard hydrogen electrode, the SHE. So there's H plus in solution, hydrogen gas being kind of bubbled in, wire to the other half cell, and a salt bridge. So this is one half of the voltaic cell. The other half would be another substance. The voltage on this wire, with hydrogen being the one of the half cells, is what's determined and reported as reduction potentials. So here are a number of different reduction potentials. This is not anything to memorize, but reference that you will use to work on problems in the notes and in your homework. So this is organized with larger reduction potentials on the top left, and then smaller as you work through the table. They're on slide 2 as well. And notice that these are all reduction potentials, so the potential for something to be reduced, like F2, gaining 2 electrons to become F minus. This is the reduction potential that would generate. Let's talk about what the standard means and standard reduction potentials, and we're just getting towards being able to use this in solving a problem. So the standard and standard reduction potential tells you that the voltage is measured by a chemical reaction under these conditions. Solids and liquids are pure substances. Solutes are 1 molar, and gases are 1 atm pressure. The standard reduction potential values of any two half-cell reactions can be combined to calculate the potential of a cell formed by combining those two half cells. So we can calculate, just to like draw this really rudimentary, we have this bridge, the wire bridge connecting the cathode and anode. We can calculate the voltage of the electron flow in that wire bridge using these values here. So that's what we'll end up doing. For a cell, so to calculate the cell potential, again, just another drawing so we can visualize this a little better. This is the wire, and we're calculating the voltage on that wire from the movement of electrons through that wire. We have anode, cathode, and then salt bridge, but really we're worried about and calculating how much voltage can be supplied with different substances, different half-cell reactions. So the standard reduction potential of a voltaic cell is the standard reduction potential of the cathode half-cell minus that of the anode half-cell. Remember that the anode is where oxidation occurs. The cathode is where reduction occurs. So any reactant in the table, now I just said table 19.2, this is the table number in your book, but it's the table that spans across 2 pages in our notes. A reactant will react spontaneously with any product that's lower on the table. Reactants near the top that have more positive standard reduction potentials, you can think of it as a higher potential to get reduced. Reactants near the top are powerful oxidizing agents. They will easily be reduced and oxidize something else. Products near the bottom are powerful reducing agents. They will easily be oxidized and cause something else to be reduced. Let's go back to the table and look at that a little better. Reactants near the top. So let's use a highlight. That'd be F2, CO3+, MnO4-. All of these are, going back to the slide, powerful oxidizing agents. Remember that whatever gets reduced is the oxidizing agent. So these are easily reduced. They are good at oxidizing something else. They will very easily gain electrons. Then the statement said products near the bottom of the table. So let's just go to the end of the table. And then look at these products. All of these are powerful reducing agents, meaning they are easily oxidized. Okay, back to our slide here. Now, this is helpful because you might not be told which substance gets oxidized or reduced. But here's an example. We have this, well, let's say we have these 2 reactions. We know we'll be using iron and nickel to create a voltaic cell. This reaction, this first one here, iron 3+ with an electron becoming iron 2+, has a higher standard reduction potential than this one. That means Fe3+ is better at being reduced. That means Fe3+ and Fe2+ will be the cathode area. All right, sorry for the wonky writing, but we don't have a lot of space. So because this standard reduction potential is more positive, that tells us iron 3 plus is a more powerful oxidizing agent. Which means it's better at being reduced, which means it will be at the cathode. Because this is more negative, nickel will be the anode, meaning it will be oxidized. Okay, so the next two learning checks, again, we're not going to do them here, but just to like give you some context for them. This one, identifying the strongest reducing agent in this list. So be sure to look at reactants and products. And then here's where you're actually calculating the cell potential. That will be it for this video. We'll cover the next section when we're actually in person.